Hello friends, welcome back. So I hope you remember me. So we'll continue with the continuation of the chapter 1. So far we have seen how to calculate the strength, how to calculate the load, and some basics of the limit state method. Okay, so we will see in detail. I will give you more introduction and more details at the end of the total RCC is completed. I will try to give a simple building, how to design even a building, starting from how to calculate the load, how to calculate the strength of the structure, and how to decide the beam dimension, everything. So at the end, okay, so far I am expecting you know some basics about limit state method, some basics about what are the strength, what is load, and how to calculate the overall load, how to calculate the overall strength in the sense characteristic strength of concrete it is Fck and steel if it is Fy, yield strength. Okay, so now I have to continue from the chapter 2. Chapter 2 I have to give some design basics and fundamentals before going to design, but have some clarity and I have some experience. No student will understand about beams, slabs, and minimum and maximum reinforcement. So much of confusion if I give the details before. So I am going to put this chapter 2 at the end of beam slab design. If you know how to design a beam, if you know how to design a slab, if you know how to design a column, at the end of all the designs we will be able to understand this chapter 2. Okay, so we will come to this chapter 2 at the end. Don't worry, this when you read this chapter 2 at the end of all my videos you will learn in some 10-15 minutes, but if I ask you to see this now, you have to memorize so many things, you will lose. Oh, why I am seeing all these things, like that you will have a feel. Okay, so we will go to this chapter at the end. Okay, so now we will start with the beam. Okay, we are going to concentrate on beam today, and in the beam we are going to stress more on singly reinforced section for the today's section. Okay, so in this section, first obviously you know what is a beam. Okay, beam is a structural member. Beam is a structural element that primarily resists load by, if I apply a load laterally to the beam. Okay, laterally, because if you in lateral direction, so you can see the image here, GIF here. If you see, the load is applied in, this is a longitudinal direction, and the load is applied in lateral direction, the beam bends. Okay, beam bends in the load applied direction. So the beam is resisting the load, the beam didn't fail. So the beam resists the load only by its lateral resistance. Okay, so this is called beam. The beam will transfer the load applied to the beam by its bending action, and it will transfer the load to the support at the end. So I hope you know what is beam. Okay, this is very clear, and if I want to show you something, so I hope you know I have showed some videos at the first video. So this is called beam. In this build you can see the lateral dimension is a beam, and if you see this bridge structure, these are deck beams, and in port and harbor structures I think I showed some video how the beam. I wish to show you this video also. Okay, if you see in this video, I hope this is called beam. This is the bed beam, and this, if you keep on going, this is a column, this is a wall. I think this is a beam. We are going to design this beam, okay, in this class. Not exactly the perfect beam, but we will understand the basics of that beam. Okay, so coming back, I hope you know what is beam now. Okay, the beam that resists the load by its lateral bending action. Okay, if in your strength of material classes you would have studied what are the different types of beam. So based on support conditions, if you see, it is a simply supported beam, it is just simply supported. If it is a fixed beam, it can be a continuous beam, it can be overhanging outside, it can be pinned beam. Pinned beam more it is common in steel structures if you have a bolt or pivot connections. So on cantilever beam, obviously I hope you know all these things, and I assume you know some basics about beam, some basics about shear force bending moment, and some basics about bending theory in strength of materials. Okay, unless it will be very little difficult to understand, but I will try to manage to make sure you understand. Okay, if you don't have that much knowledge about beam in bending theory. Okay, so this is the based on support conditions, you have different types of beams. Based on reinforcement, that's what we are going to see: single reinforcement, double reinforcement, flanger beams. There are three classifications you should remember. Singly reinforced, so you can see the figure at the right side bottom, there are so many red color bars are there. So this is doubly reinforced beam, actually this is a deep beam. Okay, so you have a reinforcement at the bottom, top and bottom Okay, so if it is singly reinforcement, you will have a reinforcement only at the bottom. Why bottom? That we will see little later. I hope you know already, because of compression at the top and tension at the bottom. Okay, so we will concrete is very weak in tension, so we will provide a reinforcement at only at the bottom. So that is singly reinforced section. Doubly reinforced section, we will have reinforcement at both top and bottom. Flanger beams, it will be, okay, there is a spelling mistake, it is flanger beam, sorry. A flanger beam, the flanger beam is nothing but there will be a beam monolithically casted with the slab. Okay, so I will give you more real time pictures when we come to flanger beams, so that you will understand more. So I hope now at the end of this slide, I hope you got clear what is beam, what are the different types of beam based on support condition, based on reinforcement, what is different types of beam. Okay, so to stress more, I have shown here some photos I have taken. So you can see the singly reinforced beam has a, you can see the left side figure, a singly reinforced section has only reinforcement only at the bottom. So this is B is the width of the beam, D is the effective depth of the beam, and H is the overall height of the beam in this figure. Okay, so you see in doubly reinforced we have reinforcement at bottom and top. Okay, I hope as a civil engineer so far in your engineering students, you know what is single and double. Okay, you can see this figure, second figure, this is, there are reinforcement bottom and top, this is a doubly reinforced section. The real time picture is also there at the right side bottom. You can see the flanger beams, how the flanger beam looks like at the right side top figure. So there are 2 reinforcement at the bottom, 4 reinforcement at the top. Actually this circle in you are seeing in the figure, flanger beams figure number B, you see that rectangle piece is a beam. Okay, and the left side and right side bars are nothing but a slab. Okay, so they have monolithically casted beam and the slab, so this structure will behave as a beam. Okay, the slab also, some portion of the slab will also bend along with the beam, so it is called flanger beams. Okay, so we will see more in the flanger beams topic. For now you see the real time picture. What I have shown here is a simple cantilever beam. I think so, yes, maybe it is a terrace. So this is a doubly reinforced section, that's what you should know now. Okay, so if you have any doubt you can ask me. I have given a mail ID at the end of this slide, you can use it to ask me. This is single, this is double, and for more stressing that nobody uses singly reinforced sections, this is only to develop a theory, and they will apply this theory to doubly reinforced section for slab, footing design, everything. We will use the same theory what we are going to see today. Okay, so I am telling you very clearly, if you understand the theory of singly reinforced section, everything will be over. All the chapters 50% you can understand very easily. Believe me, I am spending 4 or 5 minutes in this singly reinforced to make sure if you understand the theory. I promise you at the end of every sections I will show you, if you know singly reinforced clearly the theory, you doubly reinforced will take only 5-10 minutes to understand, slab will take only 20 minutes to understand. Everything, if you have 10 steps in all the chapter, 4-5 steps will be coming from this singly reinforced section chapter. Okay, so in this slide I have make sure you understood what is singly reinforced, what is doubly reinforced, what is flanger beam. Okay, so we will going inside this chapter. This is the section we are going to see today, is singly reinforced section again. So I already told you it's a singly reinforced beam. The beam is provided with steel bars on only on one side, but it is not really practical. So it is provided on both sides to have some stirrups connection to resist shear and all. For theory we are going to tell singly reinforced section, we have reinforcement only at the bottom. You see the right side figure. So the small d is the effective depth of the beam. So we will measure the effective depth only from the top of the beam to the center of the reinforcement. Capital D is the overall depth of the beam, B is the width of the beam, AST is the area of the steel reinforcement. Okay, so in overall area of this rectangle, how much area the steel is occupying, that is the percentage of steel we will discuss later. AST is nothing but how much area of the steel reinforcement it is occupying in the overall beam, this AST, area of steel. Okay, so I hope I have discussed same thing again and again for 4 minutes. You know what is singly reinforced section, how the beam will look like at the end. Okay, so in this chapter what is our plan, what we are going to see. So what we are going to see is, we at the end of this chapter you will able to do 2 things. Either you can design yourself a singly reinforced beam, or you can analyze the singly reinforced beam. What is design? What is design means, if I am giving you some moment, I want a beam to resist some 100 kilonewton meter. or 50 kilonewton meter. Somebody is coming and telling you, so they want to design a beam for 50 kilonewton meter. Then what you should say, you should reply them. So the beam size should be 300 with 20 mm bar, 4 bars or 3 bars, 2 bars at the bottom. Okay, so you should answer them this B. In the right side figure you see, if somebody is giving you the moment, you should able to tell them the B, width of the beam, D and small d and AST. Those things you should able to tell. That is called design. Clear? If somebody is giving you moment, I want to resist this much moment, you should tell them this should be the beam dimension and this should be the number of reinforcement to resist the moment you are telling. Okay, that is called design. So at the end of this chapter, I hope you will able to do that. What is the second question somebody gonna ask you? What is analysis? What is analysis is, if somebody is giving you the beam, already you know the beam. Consider if you are sitting in your house listening this, so you see the top corner, you just lift your head, turn right or left to your top corner, that is the beam. Okay, hopefully if you are in a residential building, it will be some 300 cross 300, 300 cross 400 beam. Okay, that's what you are seeing above the windows. So that beam will able to so if you know you have seen the beam now, and mostly the residential will use some 16 mm bars or 20 mm bars. So if I am giving you the beam, or you are seeing the beam 300 mm width, 400 mm depth or 300 mm depth with 4 bars, okay, at the bottom. So if somebody is giving you such beam, or the beam you are seeing above your window, you should able to calculate the how much moment it is taking now. Okay, it's very interesting, right? This even I feel like, you see any beam outside, or you imagine a beam, if somebody is giving you 320 mm bars, 20 mm bars, 4 bars at the bottom, something like the figure right side I showed you. If somebody is giving you this beam, you should able to tell them, okay, so this is the beam, I think it will take around 150 kilonewton meter, or see, don't tell some numbers like 1000 kilonewton meter. No beam will take. Okay, and it is not very practical. Okay, that will be coming under bridges or port structures. You will have deep beams. For residential buildings, 100, 150, 200 itself, 200 itself a very big number. 234, 300 and all, it will come only for very big apartment buildings. Okay, so the answer will be around 100, 150, 30, 40, 50 for small residential buildings, something like that. Okay, so be clear with this answer. Okay, coming back, analysis, I hope you understood. Somebody is showing you the beam and asking you, come on man, how much moment it will take? So you will able to tell, it will take some 70 kilonewton meter, it will take some 60 kilonewton meter. Okay, so this is the two difference. You can rewind the video and you can listen what is design and what is analysis. At the end of this chapter, after this theory, you're gonna able to tell how to calculate this design and analysis. Okay, so going inside, so first you should know some assumptions in RCC before going into, see, we are going to see divide this chapter into, I will go back to the index. So this is the index you should see. First I will teach you some assumptions. What are the assumptions they made to derive the equation? Second, what I'm gonna say you is how to derive that equation. Deriving that equation is very important, because in GATE some 2005, 2010, 2013 there are some problems I will show you. In that problems they have changed the total philosophy and asked you to derive and get your own equations and solve the problem. So in GATE exams, not only in GATE exams, so I have some more examples in railways. I have taken questions, I will show you at the end. I have shown you military engineering service. I have taken questions from everywhere for this RCC. Especially GATE is little more technical, more high level questions will be asked. For that, they have asked questions such that you should know even the derivation. Okay, so and this derivation, as I already told you, will come under doubly reinforced slab everywhere. So this derivation is very important. You can rewind 4-5 times back, or you can get this notes from any standard book. Okay, I will make sure you will understand this in this less than 30 minutes. Okay, so these are the headings we are going to see: assumptions, equation derivation, neutral axis features, and miscellaneous some topics, and we will solve some around 10 problems. Okay, today itself. Okay, make sure you have a paper, pen and calculator at the end of this chapter. Okay, so we are going to solve some 10 problems at the end. Okay, so coming back, I told you there are 5 topics. Okay, first we will see some assumptions. 4-5 assumptions are there. The first assumption is Bernoulli, Euler-Bernoulli's beam. I hope in strength of materials you would have learned some point. I hope you remember the plane section remain plane even after bending. Okay, I hope this you would have listened so many places. That was the assumption made by Bernoulli. Okay, Euler Bernoulli beam, we will say, means that. Okay, so what does it mean is, you see this, I will come back to this. You see this figure, the second figure is a strain diagram. You see it is looking like a two triangles joining at the neutral axis. So this triangle beam, if you see, what the plane section, the plane, if you okay, so I don't have a methodology to explain. Please close your eyes and listen for a minute. So you have a beam. Okay, just imagine a rectangle beam, and I am having a plane. I am cutting a plane in longitudinal direction. Okay, plane means I consider I am having a line, I am drawing a chalk piece line, or a black marker line. Okay, so if I am bending, okay, if now I am bending the beam, you are imagining I am bending the beam, the marker line I have drawn will be in the same location even after bending. Okay, this marker line I have drawn, it will not go irregular. That's what the Euler Bernoulli imagined. So before distortion, or there won't be any distortion in the shape. Okay, before bending breaks, the marker line, the plane section, remain in the same plane, it won't go up and down. That's the best assumption. Without this assumption, there won't be any strain theory. Without strain theory, there is no working stress method. That the same strain theory we are going to use for limit state method. Sorry, totally confused. Even stress was assumed as a linear in working stress method. Okay, that is another big difference. I will tell you in 2-3 minutes. So I hope it is clear. Euler Bernoulli's first assumption is, so the strain distribution is linear because the plane section remain plane even after bending. So if you see, there will be a zero strain at neutral axis and maximum strain at the extreme fibers. So this assumption will give you a figure something like this. This is what you can see, the second figure, in between figure. This figure came only from the Bernoulli's assumption. Okay, so you can rewind and back or Google something, or if you have any doubt you can ask me. Second thing is, limit state method is a strain oriented approach, a second assumption. And even in working stress method, I am showing me one more time. So you see this figure, the second figure is triangle, looks like a linear line. Even in working stress method, even the third figure is a stress diagram, second figure is a strain diagram. Even the third figure will be, it was looking like a triangles. Okay, so it was upper and lower triangles even in strain diagram. So coming back, I was telling you something about strain triangle. This is the strain triangle. The second triangle assumption came from Bernoulli's assumption. In working stress method, the similar triangle was there in for stress diagram also. Okay, you can see a stress strain diagram for a RCC beam in a working stress method. Both were looking like a triangles. Okay, but so it was stress oriented approach. Remember that. That's what I want to say. In working stress method, it was designed based on stress. It was a stress oriented approach. Here the second assumption was limit state method, we will be designing based on strain oriented. You will see how the strain is used in every derivation, every steps. Okay, so third assumption, they have decided this modulus of rupture formula. Modulus of rupture is based on 0.7 root of FCK. So I hope you know what is FCK. Last class you can remember I told you about the 100 cube stories. So from there you know the characteristic strength of the concrete. Okay, so you take the square root of that value, multiply by 0.7, you will have a tensile strength of the concrete. So this formula is highly used in designing of the rigid pavements. In the rigid pavement, it is a concrete pavement road. To have a final check whether the stress is within control, they will use this formula, and this formula will be used everywhere. If you forget, if you don't, mostly the concrete is good in compression, concrete is weak in tension. So how much weak it is, so you can use this formula to find. Okay, so for an example, if you say, if you put FCK is 40 MPa, FCR equal to 0.7 root of FCK. If you put FCK is 40 MPa, so FCK is 40 MPa is nothing but so it can take, you can multiply MPa to kilonewton per meter square, you will know how much kg it can take. So it is very high number, and I am taking a calculator, give me a second. It is 0.7 and root of 0.7 square root of 40 will give you 4.4 MPa. So you see, so the tensile strength of the concrete, for if it is compressive strength is 40, but the tensile strength is only 4, it is almost give me a second. So it is almost 10 times reduced. Okay, so the tensile strength of the concrete is 10 times lesser than its compression capacity. That's what this formula says, and this formula is valid according to IS 456. So this is the third assumptions we have in fourth assumption. So I have to explain you clearly. Please listen. This graph and this formulas we will be using in the problems later, and that's what I told you from initial. So how they derived to the final formula what we have now. Okay, so you see this one, this graph, this is the stress strain graph of a concrete. I hope you know steel, that is coming in next slide. This is the for the steel, this is for concrete. So if you see this parabolic curve, what they have written is FCK. FCK, I know it is a, I hope you know now, it is a cube compressive strength. Okay, I have written wrongly here, it is not comprehensive, it's a compressive strength. So FCK is a cube compressive strength, it is a cube strength. Okay, so you cannot, if I am making a cube and I am keeping under a cube testing machine, I am getting some 20 MPa. That 20 MPa, no need, so don't imagine if you are using the same mix design, you won't get the same value if you are having casting a beam or a column. Okay, so beam and column has a slenderness, very high slender, right? It is not a simple cube, it is a big rectangle. Okay, so when the slenderness value is getting higher, I hope you know what is slenderness. It is like lateral dimension to a longitudinal dimension. For cube, all the dimensions are same. So you are getting FCK. So when you are keep on increasing the slenderness ratio, you won't get FCK. So if I am breaking a cube, I am getting 20. If I am breaking a cylinder, what is cylinder? Cylinder slenderness ratio is approximately 2. Okay, for cube slenderness ratio is 1, lateral by longitudinal. For cylinder, circle will be very small compared to its length direction, so it will be 2. For if I am increasing the slenderness ratio, I won't get the same 20, I will get somewhere around 16. If I am increasing the cylinder length to 2 meter, 3 meter, so if I am keep on increasing the slenderness ratio, so at a certain level you will see that only I will get 0.67 times of FCK. It is something around, if I am using a 20 FCK 20 cube, I will get FCK 20. Okay, so but I am multiplying, give me 1 second. So if I am using a FCK 20 cube, FCK 20 cube, I will get, when I am breaking a cube, I will get 20 MPa. But if I break a cylinder of slenderness ratio 4 or 5, so I will have only 13 MPa, I won't get 20 MPa. So remember that the concrete column or a beam fails at 13 MPa itself. So you cannot use FCK for designing a structure, because your structure is not going to take up to FCK. It can take, this is the 0.67 FCK is the maximum strength it can take. Okay, so this is the ultimate strength. From there you will apply a partial safety factor, what we studied in the last class. So 1.5, you divide the partial safety factor, so the design compressive strength of the concrete is really, it is 0.45 FCK. Okay, I hope it is clear. I hope I made you clear all the values on the right side. On the graph, it is FCK 0.67 FCK and 0.67 FCK divided by partial safety factor. This value, this 0.45 FCK is the max, is the design value we will use for designing a compressive strength of the cube, compressive strength of our beam. Okay, and you see the strain side, it is in the x-axis. Strain, if you see up to 0.002, all the strain, it was linearly increasing. After when the stress is increasing, the strain is also increasing linearly. After the strain in the cube or a concrete or something, if it reaches a 0.002, if I keep on increasing the stress little by little amount, the strain is already, it reached the maximum strain. Okay, the structure totally collapse. You can see the straight line. This is the assumption made in IS 456, again to make it as a straight line from 0.002 to 0.0035. Okay, so the breaking, the value at which the concrete breaks, the strain experienced by the concrete specimen when the cube or beam breaks is 0.0035. This is the maximum strain a concrete will experience, and 0.002 is a very critical value, because beyond this value it won't take any more stress. The line is, you can see the line becomes straight. Okay, so at the end of this slide, I hope it is clear what is FCK, what is 0.67 FCK, how it came, and why we are dividing by partial safety factor, and what are the two strain values for the concrete, what is 0.002, what happens after 0.002, and what is the maximum strain in the concrete. Okay, so you see the last line. So how much factor, overall factor of safety we are assuming for a concrete, because we are not taking, if I am breaking a cube I am getting FCK, but I am gonna design only for 0.45 FCK. Okay, so I am assuming overall factor of safety for the concrete I am taking 2.22. Okay, okay, so similarly I am going to explain the next assumption for steel. So in steel, if you see similar, there is a stress strain graph. Okay, we are going to see max. I hope you have studied about the mild steel stress strain graph. It is the stress strain graph given in IS 456. You can see, as I explained earlier, how the FCK, from the FCK you have reached 0.67 and then you reach 0.45. Similarly here you have reached FY. Beyond this, if you apply the load, all those things will happen, strain hardening, plastic zone reach, and then rupture, everything will happen. So we are having a graph only up to Fy. So if you see in strain stress, the value will reach up to Fy. Then Fy is a yield strength of the material of the steel. So now I apply a factor of safety 1.15. Then the design strength of the steel, what I will use is 0.87 Fy. It won't be 0.45 CK. Okay, I hope it is clear. For design strength of the concrete we used 0.45 FCK, design strength of the steel we are using 0.87 FY. Okay, so I hope you understood how we got this number. You can also see the x axis in the stress strain graph. It is 0.002, 0.002 and 0.004 and 0.006, like this. Okay, so you have also, you can see the strain value in steel when the design curve 0.87 Fy is reaching. Beyond that it is becoming a straight line. The strain is 0.87 Fy by Es. What is 0.87 Fy by Es? 0.87 Fy is nothing but a stress. Es is Young's modulus. So stress by Young's modulus is nothing but strain plus 0.002. Okay, so you there is an explanation here in the left side, you can see. So you all the stress and graph in the limit state method are considered to be elastoplastic. If the concrete is reaching the strain of, you can see in the previous slide, the beyond, if the concrete reaches 0.002, beyond, if you apply a single point of stress, it will collapse reaching 0.0035 because the line is straight. Okay, so we should assume that strain in steel should be more than the 0.002 such that concrete will not reach the 0.002. Okay, so they have taken an assumption. If the assumption how to calculate the strain is, how you should design is, strain in steel should be always greater than 0.002, because either concrete will reach and there will be a sudden collapse, because if your concrete reaches 0.002 then there will be immediate collapse. So the strain in steel should be greater than 0.002 plus the material's own Young's modulus and Fy. Okay, so you have a clear explanation here. You can see this will be the strain value we will be using for the maximum strain value we will be using for the steel. Okay, like how you have here maximum strain is 0.0035. So like that we will use strain in steel, maximum strain in steel will be taken from this values. Okay, so you can pass it and you can understand how this number came. If you have any doubt you can mail me. Okay, so I hope you have clear idea about all the assumptions we have taken. Okay, all the 6 assumptions. So now we will start the derivation. It's just a 6-step derivation. It's very easy. You see the right side figure, just memorize this figure. This is a singly reinforced beam. You have 3 reinforcement at the bottom, that is AST, the effective depth D, width of the beam is B, and I hope from the bending theory you studied in strength of materials, you know the dotted line is a neutral axis. Above the neutral axis is compression, below the neutral axis is tension. Okay, I hope you know that. If you bend a beam, top fibers compress, bottom fiber expand. So the reinforcement is provided only at the bottom. Why? Because concrete, I showed already, I have discussed, it is very weak in tension, so it should not fail in tension. So to avoid that, what we will do is we will insert the reinforcement at the bottom, so that we will assume that tensile tension which is coming because of bending will be taken care by this steel, such that the concrete will not take any tension. That is another assumption in IS 456. Okay, the concrete will not take any tension below the neutral axis. The steel will take the tension. So that you see the third figure, you see there are three figures here. Third figure, there is no any diagrams here. So only stress diagram is only at the top because it is for concrete. Below there is no stress diagram for concrete because concrete will not take any tension. Okay, clear? So there are three diagrams. Second diagram is for strain, third diagram is for stress. Okay, so now I hope I made you clear. This is the dotted line is neutral axis, below is tension, above is compression. Below tension is made of three steel bars, that is AST, and it is will be taken by only by the tension T. Okay, so strain diagram also, if you see, and I will make sure it is clear, the above the neutral axis is compression. Okay, compression means compression is totally taken care by concrete. So you see the strain diagram, it is a triangle. That triangle came from the assumptions we made, this 0.0035 and 0.002. This parabola shape in the stress diagram for the concrete came from this parabola shape. You can see the parabola shape, the third line from the top, you see 0.67 FCK by gamma m. This parabola shape came here directly for the third figure. Okay, so this 0.45 SCK I have explained, 0.0035 I explained, 0.002 I have explained. So if you see the rectangle at the top for the compression, you have two values, 1 and 2. So the 1, I am dividing the rectangle into two sections, 1 for the rectangular portion, 2 for the parabolic portion. Okay, so again, to make sure you understand, you see this figure, in this figure up to 0.002 is section 1, I have assumed. From 0.002 to 0.005 I have taken as a section 2 because it is a straight line. So the figure at the third graph, you see, the third line you see, so one section looks like a rectangular square, one section looks like a parabola. Okay, so you coming back here, I hope I made you clear. The section 1 is for that rectangle thing, 0.0035 to 0.002. Section 2 is for this parabola thing. Okay, so you go back and come and sit and realize and understand the figure. If you didn't understand the figure, you can never understand anything in the next slides. Okay, so step 1, I am taking the strain diagram. I am taking the strain diagram and I am doing a similar triangle. Everything is self-explanatory. You can see here the tan theta is equal to opposite by adjacent. I have taken 0.0035 by XU. Similarly, I have taken a similar triangle for the bottom triangle. So I have taken a similar triangle from the neutral axis. So there are two triangles. One is up to 0.002, one is up to 0.0035. From that I could able to find what is x1 and x2 in terms of xu. Okay, so it is 4 by 7 of xu. How 4 by 7 of xu is just divide 0.002 by 0 those things. Okay, I hope you know this calculation. So step 1, find the value of x1 and x2. Okay, how in the total neutral axis of xu, how much is x1, means what is x1, how much is the length of the parabola and how much is the length of the rectangle. Okay, so step 1 is over. Step 2, tensile force. What is tensile force? Is nothing but a stress into area. We know the stress is 0.87 Fy. Okay, that is the stress value I have explained in the previous slide. 0.87 Fy is the stress and area is AST. So AST is nothing but area of the steel. So stress into area will give you the tensile force. So if you know the how much reinforcement you are putting in the beam, so you take that area, multiply by 0.87 Fy, you will get the how much force the beam can take. So going to next slide. So now in step 2 you have, I hope you understood how to calculate the tensile force. Now coming back to compressive force. Compressive force is divided into two sections, as I told you, 1 and 2. So one section is for parabolic portion, one section is for rectangular portion. So for parabolic for a rectangular portion is C1. It's very easy. It's just a rectangular area. So stress into area, I hope you know stress into area is the force. For stress for throughout the rectangular area, it's 0.45 FCK. You can go back to the figure and see 0.45 FCK is constant throughout the section 1. So stress is 0.45 FCK and area is rectangle. It's very easy, B into x2, length into breadth. Similarly for C2, it's a parabolic area. It's 2 by 3 of BH. So for 2 by 3 should come back. Okay, stress value is same, 0.45 FCK into area is 2 by 3 of B into x1. So stress into area for C1, stress into area for C2, add both, do the algebra, so you will get the final value 0.36 FCK B into XU. You see the C value, final C value is again stress into area. What is stress here? 0.36 FCK. What is area? B into XU. If you see what you can see here, what is B into XU? B is the width of the beam and XU is the overall concrete area. Okay, so it's very clear. B into X is the overall concrete area above the neutral axis and stress is 0.36 FCK. So take a break, take a pause, derive yourself how this one came, then you can go next. Okay, so I hope you are sure that from FCK we came to 0.67 FCK, from 0.67 we came to 0.45 FCK, and for y from 0.45 how we got to this 0.36 FCK. So if you didn't understand, please don't go to the next slide, pause, try to understand, go to the videos again and again, and then try to understand from FCK how you reached 0.36, then you can understand the next things. So I hope now you know what is the compressive force and what is the tensile force. Okay, so but this is rectangle and parabola. Okay, so still you don't know where, you know the force but you don't know where it will act, because the COG for rectangle is different, COG for parabola is different. So we are going to take a moment of area to determine where exactly this the C value what we calculated here will act. So it is very simple. It is less, if you know the formula from engineering mechanics, A1 x1 plus A2 x2 divided by A1 plus A2. I will apply everything here. You can see C1 from the previous slide, you can see C2, everything you know. Y1 is the distance from top of the fiber to the center of the rectangle. Y2 from the top of the fiber to the COG of the parabola. It is, so you substitute everything. You see this slide, you take a pause and you derive it. You will know that the compressive force will act at 0.42 of XU from the top of the fiber. That will be your final answer, Y bar. Y bar will be, you if you solve this algebra, you will come to know, you will the compressive force will act at 42%, 0.42 of the neutral axis from top of the fiber. Okay, so using this, here it ends, the derivation ends now. So under all the circumstances, we will come to that point later. Under all because till failure, C should be, you see the left side figure, the compressive force and tensile force should be same, or else the beam will collapse. You understood, right? It's a, we are going to bend the beam. If you are, when you are bending the beam, if T is more, the bottom piece will pierce out. If C is more, top will get crushed. So before failure, always the C and T should be same, so that the bending will be equal. That's our another assumption. Already I have discussed that. Okay, so you should remember the C equal to T. Always that C value what we calculated above, this 0.36 FC can be into XU, will always be at any moment will be equal to this 0.87 Fy AST. Okay, so coming back to the final equation, what so far last 30 minutes you are sitting in front of the laptop or something to only to know this formula. If you didn't understand anything, skip everything, just memorize this formula. Okay, so the compressive force, based on compressive force, moment will be equal to, I hope you know what is moment. Moment is nothing but force into distance. The force we have calculated is 0.36 FCK. 0.36 FCK is stress, B into X is area. So stress into area into distance. What is the distance? So if you know, if you see the left side figure, D minus Y bar is the distance between the C and T, because the moment which is about to generate is the distance. Moment is nothing but force into distance, it is not a force. Okay, so the rotation, the rotational distance is D. Small d is nothing but the effective depth. If you see small d, this is, you see this figure, the small d, I am subtracting, you see the first figure, small d is from the top to bottom of the reinforcement, and Y bar is the distance from top to C central point. If I subtract d minus that Y bar, you will get the distance between C and T. Okay, the distance between where compressive force is acting, where tensile force is acting, that is d minus Y bar. So Y bar we have calculated 0.42 into XU. So d minus 0.42 into XU is the distance. So it's very simple to memorize. Moment is nothing but force into distance. Force is 0.36 FCK B into XU. Distance is d minus 0.42 into XU. Okay. So it's not a big formula. I hope again I am dividing it. 0.36 FCK is stress. B into XU is area. Stress into area is a force. D minus 0.42 into XU is a distance. So again, based on tensile force, we can tell moment as a force into distance, T into L. T is already we have calculated 0.87 Fy into AST. L is same distance, D minus 0.42 into XU. Okay, so as we discussed earlier, for the beam to be stable, the moments generated because of compressive force should be equal to tensile force, or that the beam will distort. Okay, as per the elastic theory, what we have discussed so far, the beam to be stable, both the formulas should give the same answer. Okay, so clearly, again I am repeating, if you didn't understand last 30-40 minutes, no problem. For singly reinforced, this is the equation, just note down the equation. Okay, or else if you got something, go through the back and forth to understand this formula. With this formula, we are going to solve some 10-15 problems after the topic of neutral axis. Okay, that we will see in the next session. Okay, thank you.